Today we're just going to take a look at the problems on the review sheet for the test on activity 13. This covers graphing rational functions and all the algebra with those rational functions as well, including inequalities. First thing you want to do when you're graphing anything is to factor both the numerator and the denominator. You want to look for removable discontinuity or a hole in the graph. So the top factors to x minus 2 and x minus 3, and the bottom x minus 2, x plus 2. So we do have a common factor, so we definitely have a hole where x equals 2. To figure out the y value of that hole, use the reduced form and plug the 2 into the top and the bottom. So the y value of the hole is at negative 1/4. Horizontal asymptote comes from looking at the degree of the top, which is x, the degree of the bottom, which is also just an x. So now we're going to do lead coefficient divided by lead coefficient. So our horizontal asymptote is at y equals 1. I'm going to put that on the graph. Vertical asymptote comes from setting the denominator equal to 0. Please use the reduced form. So we get x equals negative 2. Put this on the graph. Be sure to use your calculator to look at the graph itself, just to help you kind of verify if it's correct. X-intercept, you set the top equal to 0. So we get x equals 3. So if x equals 3, then y equals 0. For the y-intercept, you make all the x values 0. So we get y equals 0 minus 3 over 0 plus 2. So our y-intercept is 0, negative 3/2. Now the last few questions here in the list deals with the actual graph itself. So I'm going to draw the graph first and then answer the questions based on that. You could also just look at the calculator if you want to. There's our x-intercept, y-intercept. The hole in the graph is at 2, negative 1/4, so just a tiny bit below that x-axis. You can either put the hole in there first or put it in after you draw the branch. So this branch, this bottom right-hand corner, has all the points, which kind of helps you understand how the top left-hand corner will look as well. So we just draw that in without any values at all, and no points. So now as we look, as the graph goes to positive infinity, so this is where the graph is heading towards positive infinity, the y value is heading to positive 1, but from the bottom, or from the negative values. I don't know what that is, sorry. If we look at the graph going the other way, if we look at the graph going out here to negative infinity, the y values are also approaching positive 1, but from the top. So this will be 1 from the top, or from the positive side. As we take a look at the graph approaching negative 2 from the right, so negative 2 from the right is this way. I'm coming at negative 2, so you can see that the y values head towards negative infinity. And if I come at negative 2 from the left, that's over here, and that means the y values are going to infinity. Some of those questions you may not have answered before, but it is just about reading and reacting to the graph. So we'll definitely have a slant asymptote here. Not only are you told that, but you can see that the power on the top is higher than the power on the bottom. So we're not going to factor this because it's not factorable. We're going to use long division. Be sure to fill in any parts that are missing. X squared is there, the x term is there, and the plane term is there, so we don't have any zeros on this. You want this term to match the first one underneath the division sign, so we're going to multiply by 2x in order to make those two things match. Now you distribute, and 2x times 2 is a 4x. Changing all the signs on the bottom, now you add. So of course what happens is this is eliminated, and now we have negative 9x minus 3. Then you start all over. Now we want this to match the negative 9x, so we'll multiply by negative 9. Distribute, you get negative 9x minus 18, changing the signs on the bottom. We do have a remainder, which we do not care about. So the slant asymptote is the line y equals 2x minus 9. Here you're asked to kind of put the parts back together. So if you can find all these things, The assumption is that you can put it back in. So we're going to write an equation for a rational function. So we know we have a fraction. I'll give it a name. Has removable discontinuity at x equals 1. Well, what that means is we have a common factor, top and bottom. We have a vertical asymptote at x equals 5. Vertical asymptotes come from setting the denominator equal to 0, so we'll make that into a factor. You do not need to multiply it out. Certainly don't reduce it, because then we won't see the x minus 1. Let's try number 4. We're going to write an equation again for another rational function. We have a vertical asymptotes, or two of them, one at x minus 6. This will be x plus 6 in the bottom, x plus 2 in the bottom. X-intercepts come from setting the numerator equal to 0. So that's going to be x minus 2 and x minus 1. These factors don't match top and bottom, so we haven't created a hole accidentally or anything like that. Horizontal asymptote, the degrees match. Right now we have x squared over x squared. So if we want our horizontal asymptote to be at 8, we'd have to create a situation where we have 8 over 1. So I'm just going to put the 8 in the numerator. Here we're just going to read the graph and do some more end behaviors. But this is specifically left side and right side behavior around the vertical asymptotes only. So our two vertical asymptotes are at x equals 2 and x equals negative 2. So since that's our focus, sorry about the extreme wiggle, we're going to pay attention to x approaching negative 2 from the right, x approaching negative 2 from the left, or top and bottom, depending on how it looks. Then we're going to do the other vertical asymptote, which is at positive 2. So x approaches positive 2. I'll go from the right again. And then x approaches positive 2 from the left. So here we are, it's all set up. All we have to do now is read the graph and fill in the numbers. So x equals negative 2 is over here. And as we come at it from the positive side, from the right side, that's this one. So we know that it's going up. That's infinity. At negative 2, if we come at it from the left, you can see that it's going down. So that's negative infinity. For positive 2, 2 from the right, so over here is the positive number. So we're coming at it this way. As we get there, it goes up. So that's infinity. And from the left-hand side is over here. And as we approach that positive 2, this heads down, which is negative infinity. So be sure you use your vertical asymptotes. If you have one or two vertical asymptotes, be sure to use them both. Solving rational equations. This is where you want to multiply by the common denominator, or you could cross multiply if you have a problem like number 7. So here our common denominator has to have one of every piece. So our common denominator is actually x minus 3, x plus 3. So we're going to multiply 1 by that. Well, that's pretty easy to do. I'm just going to write it x minus 3, x plus 3. That's times 1. If we multiply this middle one by x minus 3 times x plus 3, the x minus 3's cancel. So we have plus 3 times x plus 3. And if you multiply the 4 by that same common denominator, everything cancels and we get equals a plain 4. So what should happen is you got rid of the fraction, and that's exactly what happened here. So we know that this is x squared minus 9. Distribute this 3, of course, so we get 3x plus 9, and this equals a plain old 4. The 9's are gone. X squared plus 3x. Bring the 4 over here so we can factor this. And it factors 4 times 1 is 4, and 4 minus 1 is a positive 3. So we get x equals 1. And of course, negative 4. Now you do need to go back and check that in the denominators. You can't have any situation where it'll create a denominator equals 0. So our denominators, a 3 or a negative 3 will make this a 0. We don't get a 3 or a negative 3. So both of these solutions work. Problem number 7, you could multiply by the common denominator, or you could just cross multiply, which is what I'm going to do. I'm just going to cross multiply. Doesn't matter which direction you go first. So 4 times x minus 3 equals negative 3 times x plus 2. The result is the same. We end up having no more fractions. Distribute the 4. We need to get these terms together, so I'm going to move the 3x over here. and add that. So that's a 7x. And I'm going to move the 12 over here. So I'm going to add 12 to this side. So we get 7x equals a positive 6. And we get x equals 6 over 7. Checking that with the denominators, we're still not going to get 0. So that one actually works as well. If you do get one that gives you a 0, you just cross it out. If it's the only answer, then you would have to say, well, then you don't have a solution. When you solve anything that has an inequality involved, you're going to have to use a number line and write your answer in interval notation, which is basically translating your number line. With rational inequalities, you want to factor out the numerator and the denominator. Remember, a common factor, or removable discontinuity, if you will, gets removed, and it is not on the number line because it is removed. If you just call it removable discontinuity, it might help you remember to remove it. The denominator is 5 times 1. And of course, we want the minus 5 and the plus 1. So we don't have any holes in the graph. So the numerator is allowed to be 0. So we know that x is allowed to equal plus or minus 4. The denominator is not allowed to be 0. So then the denominator says that x cannot equal 5 or negative 1. This impacts the symbols used on the number line. So let's put these in order. Negative 4 is smallest. Then we have negative 1. Then positive 4, and positive 5. So the positive and negative 4 are going to be using this symbol up here. So the positive and negative 4 are actually going to be a closed circle. Now for this, negative 1 and 5, they're not allowed to be equal to those numbers, so this would be an open circle. So they get decided based on two different things. The top uses the symbol in the problem, and the bottom is going to be an open circle. Now we're going to test a section. I'm going to use 0, and that falls right in through here. We didn't have anything cancel, so I'm going to go ahead and use the original. So we have 0 minus 16 on top of 0 minus 5. Is that greater than or equal to 0? Well, 16/5 is positive, so yes, this actually works. So this is a yes. No. Yes. If this middle section right here is a yes, then this will be a no, and this part will be a yes. And then all we have to do is translate the graph. Negative infinity to negative 4 with a squared off bracket. Union with the next interval, 1 to 4. And then the final interval is 5 to infinity. So we have 3 sections of the graph that will give us answers that work. Let's try that one more time, just for fun. Again, start by factoring the numerator and the denominator. So this has a 2x in common, leaves you with x squared minus 2. The denominator has just x squared in common, leaves you with 3x plus 4. Now this is a kind of a super weird one, because we have a hole in the graph, right? Because these two can cancel. But it leaves you with x. So it seems like we have a hole at x equals 0. And the holes do not go on the graph. But then again, at the same time, we still have this in there. So this is actually not going to be a hole. To confirm it, you could look at the graph on your calculator. But I'm not going to be able to show that to you. So we still have it here. It's still there. So when we set the numerator equal to 0, we get x squared. Remember, the numerator is allowed to equal 0. So we get x equals positive and negative radical 2. Use your calculator. That's right about 1.41-ish. The denominator is not allowed to equal 0. So x cannot equal 0. And 3x plus 4 cannot equal 0 also. So 3x cannot equal negative 4, and x cannot equal negative 4/3. Well, the ones from the top use this symbol. So that's going to be an open circle. The ones from the bottom cannot equal, so everything on here is going to be an open circle. The weird part is this 0. because it seems like a hole and it seems like a spot on the number line. So we're going to put it on the number line once we get these in order. Negative radical 2 is the smallest, because this is 1.41. This is about negative 1.3 repeating, so they're close, but this is the order. And then we have a 0, and then, of course, the positive number. So we cannot use 0, and these are all open. We cannot use 0 as a test point, so I'm going to use 1, which falls right in here between 0 and radical 2. Plugging the 1 back into the original, despite the fact that it does have a cancel, it's not going to matter because we're not going to get anything like 0 over 0. So when you plug that in there, we get 2 minus 4 on top of 3 plus 4. And is that less than 0? We get negative 2 over 7. So yes. So this section works. So this is a yes, no, no, yes, no. So this result, all of them are open circles, so we have rounded brackets, negative radical 2 to negative 4/3, so there's one interval. And we join that up with 0 to radical 2.